So as before, I'm recording this lecture for people who need to access the lecture later. It'll be posted on Moodle sometime today. Couple business items for folks who are watching later or doing it now. Some clarification on the in-class assignments. So please turn those in via Moodle, the participation assignments. And you have until the end of the week to turn them in. So if you're watching this later, you can still do the in-class assignment, turn it in online. Some of the things today are going to require some group activities. So if you're not here this morning live, then you'll just have to do those on your own and just pick one assignment of the group. So today I'm going to try a class 4 move. We're going to break out into groups. You guys are going to do something together, and then you're going to pick a spokesman or a spokeswoman, and they're going to present. So they're going to share their screen and present their results. So we're going to have people share screens. I don't know how it's going to work. It could be a disaster. We'll see. But we're going to try it. Okay, so if you're not here live, of course you can't do the screen sharing part, but you can still do the do most of the in-class assignment and just turn it in via Moodle, and you have till the end of the week to do that. So you should have plenty of time to download the video or watch it live and then do the in-class assignment and turn it in. Okay, any questions about logistics right now this morning before we get started? All right. Okay, so I'm going to share my screen here in a sec. Once I get things worked out here, and okay, so let me share my screen. Okay, so hopefully you're all seeing my desktop, and let's see if I can, if you have a question, just talk, because last time it took me a while to figure out how to get the chat screen to show up, and I don't want to take all that time and deal with it. So if you have a question, unmute yourself, talk. Let's see. Okay, so when we left yesterday, we were talking, or on Tuesday, we were talking about the Dupuy assumption. And today we're going to look at some an analytical solution. Okay, so we did all this talking about why flow in an unconfined aquifer is different than flow in a confined aquifer. So what does anybody remember any of the reasons why an unconfined aquifer was different than a confined aquifer?
Sir?
Yep.
Well, to answer your question, the same thickness throughout in an unconfined. It follows the water table, which can head to a lower head, whereas the confined because the confining layer is laid horizontally. It's all the same thickness, and the flow goes unconfined. It has an upper and a down, across, and back up flow.
Okay, so the
Did
thickness,
you get that?
yeah, in the unconfined aquifer, the thickness is not constant.
Right.
Um,
Your groundwater flow has a gradient both down and across.
all right, so we have a vertical component to flow.
Horizontal.
What are other differences between confined and unconfined aquifers?
Find it's the flow is all horizontal because the
Yeah, that's
confining
kind of
layer.
this bullet here.
Storage is different. You have to desaturate the pore space.
Oh yeah,
Yeah,
storage.
storage comes from drainage of pores. Okay, so we get these large, so not just compressibility. Okay, so these are the main differences of June would like this to be bigger. Maybe, yeah. Boom. Okay. All right, so these are the main differences. And the reason why we talked about the Dupuy assumption and deriving the Dupuy assumption. Okay. And so we talked about the Dupuy assumption. And then at the end of the day, we derived the aquifer equation or the Boussinesq equation. So the Boussinesq equation looked like this. S dH dt was equal to d dx k h dH dx plus d dy k h dH dy. All right, and the main differences were that storage S is now SY plus SS times B. And then now we also have this extra H, right? And this H changes as a function of position, X and Y, all right? So we have this extra H and it's a function of X and Y. All right, so that's our Boussinesq equation. All right, and then we use the definition of transmissivity. What's transmissivity?
It's similar to way of describing it.
It's similar to hydraulic conductivity, but it's not quite the same. What was the difference?
It's an aquifer's ability to move water.
It's the aquifer. It's
Yeah,
the
okay.
aquifer.
So it was equal to the hydraulic conductivity times the aquifer thickness B. All right. And for a unconfined aquifer, B is equal to H for an unconfined aquifer. All right, so that gives me T is equal to KH. And I can plug T in here. So I get the aquifer equation. All right, and that is S dH dt is equal to D dx T dH dx. Plus D dy T dH dy.
And so is there, or is T the same all the way through?
T changes. So, well, let's answer that question. What do you think? Is T going to be the same or is it going to change?
I think if you,
Mark's breaking up. You might want to text your answers. But what do other people think? Or Mark, another thing you could do is probably mute your video for now.
all right.
What do you think T is going to be constant or the same?
It'll change because the thickness of the unconfined aquifer will change as a position of X or Y, or really just X.
Yeah, I agree. Unless the hydraulic conductivity just by some miracle happened to change at exactly the same rate as the thickness, this is going to have to be spatially variable. We can also tell that from the differential equation. So how can I tell from the differential equation that T is variable in space?
It's still within the function. It's going to have the distributive taken on it.
Yeah, it's still in this, the T is still inside this derivative. So that means this guy can change with space. And it can change with both the X and the Y direction. All right. So it's not going to be constant. It's going to be a function of your location.
So should we have X and Y subscripts?
It depends. Yeah, you can put them in there if they make you feel better. We don't. Yeah, you could also have this if it can have. Yeah, this means that they are. Why? If I put this X and Y subscript, what does that mean there? Actually.
Just, I guess it just makes it clear that the transmissivity is in terms of X and or Y, depending on the subscript.
Okay, so why would I have a different transmissivity in the X direction versus a different transmissivity in the Y direction? What property does that imply?
Hydraulic conductivity.
Heterogeneity.
No, heterogeneity is this guy that it's inside the derivative. The fact that it matters which direction this T.
And I thought
It's Anisotropy.
All right, so this means anisotropy.
Ugh.
Okay. So yeah, putting that makes it more generic, Mark. You're right. That makes it so that we have an anisotropic. There's a lot of misspelling in there. Anisotropic. Okay. All right, so we made the Dupuy assumption. We derived the Boussinesq equation and the aquifer equation. And they're not exactly right, but they're useful. And the reason why is that we can now solve this equation. It's a thing we can solve. And so what I wanted to do now is look at an analytical solution to the Boussinesq equation for a given scenario. So let's let me think about a problem here. Let's see. I'm going to give us a cross section here. Yeah, let's make it black. All right. And so here's my land surface. Put some trees. Some grass. Okay. So let's, we're doing some research right now in my group in this exact scenario. So we've got one river on one side, and we're in an alluvial plain in between a confluence. So we've got another river on this side. So in our research group, this is the Wind River over here. And over here on this side, we got the Little Wind. And in the middle, sort of sitting right about here, there was a big uranium tailings pile. All right, and that uranium over the years has leached down into the ground and hit the groundwater system. And so one question, and that's happening. That's happening because, well, we get precip across the top here. And that results in a pretty uniform recharge across the top of our alluvial plain. So we got this uniform recharge at the rate n. Let me move that. It's too hard to see there. So we get recharge at this rate n. Okay, so the question is, we got this recharge, adding water, adding uranium, and the question is, which river here is this uranium going to discharge to? Is it going to go to the Wind River or the Little Wind River? All right, and that answer to that question is dependent upon the shape here of the water table between the two rivers. All right, so if we were, there's a groundwater divide somewhere here between the two rivers. And what we'd like is some way to tell where that groundwater divide is. So where's the groundwater divide and what is the shape of the water table so that we know which direction the uranium's going to flow. Is it going to go to Little Wind or the Wind River? Okay, so this is a real problem. Okay, so here are some boundary conditions. This river over here, let's say this is x equals to 0 here on this side. This is x equals to L. So x is increasing in this direction. This river over here is H naught. So the height of the water table here is H naught. The height of the water table on this side is H sub L. All right. Okay, so my boundary conditions. H is equal to H naught, x equals to 0, H is equal to HL, x equals to L, and N is equal or is greater than 0. And this is at the surface. Okay. So there's a solution to the Boussinesq equation with these boundary conditions, and it looks like this. H is equal to H naught squared minus H naught squared minus H sub L squared over L plus K, the hydraulic conductivity of my aquifer, over N, L minus X times X, all of this to the 1/2. All right, so this equation gives me the head at any place X along this profile. All right. So if I want to find the groundwater divide here, I can play a trick. I can say, hey, the groundwater divide is going to be the place at which the derivative of the head with respect to X is equal to 0. So right at this point, we have a flat slope. So the derivative is equal to 0. So we take the derivative of this equation, we set it equal to 0, and we find and we solve for X, and we're going to get the location of the groundwater divide. So the equation for groundwater divide, X WD is equal to L over 2 minus K over N H naught squared minus HL squared over 2L. All right, so this gives me the location of the water table divide. All right, so couple take homes. First of all, if I wanted to know where the uranium, which river it's going to go to, I just need to know its X location with respect to the water table divide. So in the case of the Little Wind River, it lies like it's in this drawing. It's on the Little Wind side of the water table divide, and we have a plume of uranium heading into the Little Wind River. All right. But the power of the Boussinesq equation is it allows me to determine pretty easily where my groundwater table divide would be and which of these rivers I should expect the uranium to go towards. All right, so that's why we make this assumption, and that's why we use the aquifer equation. It simplifies our problem enough to where we can actually solve it. One caveat and one important thing to think about anytime you use the Boussinesq equation and the Dupuy assumption is that the water table configuration in reality is different than what the Boussinesq equation. So this guy is what is predicted by the Boussinesq equation, this H. In reality, what the water table looks like, it's going to follow the Boussinesq in the middle, okay, but at the ends, it's going to have a much steeper gradient. So this is the real water table. And this blue one is the Boussinesq water table. For things like determining the water table divide, the Boussinesq is fine. It works fine in the middle of the aquifer. It doesn't work fine at the end. So if you really wanted to know the shape of the water table right near the river, using the Boussinesq equation would not be a great idea. All right. We still do it. It's the best. It's what we use all the time, but it's just something to keep in the back of your mind that the Boussinesq equation and solutions to it are not going to perfectly map the shape of the true unconfined water table. Okay. So that's going to sort of end our discussion for now of unconfined aquifers. The bottom line is that they're significantly different than confined aquifers. We have to make some assumptions in order to simulate them. In particular, the Dupuy assumption, and then we can use this Boussinesq or aquifer equation. Okay, so what I wanted to do for the next bit is shift gears and talk about this freeze paper. So this is, so the freeze paper is available on Moodle. And on Moodle, I've uploaded a Word document that has some discussion questions. So here's what I want you guys to do. And I sort of give the instructions in the Word document as well. I'm going to break you guys into groups. All right. You're going to take 10 minutes to discuss this freeze paper. And then you're going to, each group is going to be assigned one of these FlowNet images. And what I want you guys to do is take one of these FlowNet images, and you'll see how I sort of divvied it up by group. But a lot of these FlowNet images only have these dashed lines are the equipotential contours, all right? And there's no flow line. So here's a completed FlowNet. It has the equipotential lines, and the dark lines are the flow lines. So what I want you to do is complete some flow lines for one of these images. All right, so I'm gonna just do an example and show you how you can do it on your local machines. So you could open up a PowerPoint, create a new slide, all right? I'm assuming everybody's got PowerPoint on their machines or something like it. And on a Mac, I'm sure Windows has similar functionality. I could take a screenshot real easily, say of this FlowNet, all right? And I can capture it. And I can bring it over into my PowerPoint. All right, so how you do this, if you're on a Windows machine, probably a little different than on a Mac, but shouldn't be too hard to get a screenshot of this into PowerPoint. And then once you're in PowerPoint, you can go to Insert, Shapes, Scribble. And now I can draw a flow line. So here, I might want to start a flow line up here. And remember that they need to follow, they need to be perpendicular to the equipotential lines. All right, so my flow line here would start here, come down, it hit this, it would rock along here, and then it would come up and discharge. Okay, and I might want to make this a little thicker. All right, and you know, drawing on the computer is hard, so we're not expecting perfection at all here. But what I want you to do is get some practice and some feel for seeing how these flow lines would follow or would be affected by the equipotential line. So I could put another one here. Oh. Start another one here. It's going to come down, hit this guy, rock along here, and back out. Okay, so here's what I want. I want each group will pick basically one of these. You're going to draw some flow paths. And what I want you to do is think about why the flow paths are doing what they're doing. All right, so for this panel, all right, I can look at the distribution of hydraulic conductivity and I can think about why everything is descending so rapidly down to this layer down here and then not coming back out of it until we're at the very bottom of, or the downstream end of our flow system. Well, here, my hydraulic conductivity is 10 times higher in this lower layer than it is up here. And the water, the groundwater, is essentially going as fast as it can down to this high hydraulic conductivity layer, all right, hitting it and traveling as far as it can in the high hydraulic conductivity layer and only coming back out into the low hydraulic conductivity layer at the very discharge end. And this happens for almost all of the flow system. It just is coming down and not coming out until the end. All right, so that's, I want you guys to discuss the freeze paper, and then each group is gonna pick one of these panels and do this. And then you gotta pick a spokesperson, and they're gonna share their screen and talk about how they got their FlowNet and what's happening, why the flow paths are following the trajectory they're following. what subsurface configuration is causing that. All right, so here it would be this low or high permeability layer at depth is causing all the flow paths to head towards that high permeability layer at depth. All right, so the freeze paper and the Moodle assignment are posted on Moodle. I'm going to break us up into breakout rooms. Now I'm going to do 4 breakout rooms, and each breakout room will do 1 panel out of, there's 4 different figures, and I have that sort of broken up in the assignment. So any questions now before we break out into breakout rooms? Everybody pretty clear? Okay, I'm going to start our breakout rooms. And here we go. If you got a question, you can chat with me, and I will drop into the breakout rooms like I did last time. All right, well, oh, and 15 minutes. So it's about 8:40 now. So at about, why don't we do, it's 8:40 now. At 8:55, I'll start closing things down. All right, check you later. Okay, so we've pulled everybody back out of the main, or out of the breakout rooms back in the main session. And so now what I want you guys to do is we'll have each group sort of show their beautiful, I've seen some amazing drawings, and mostly talk about, you know, what sort of flow paths they got and what observations they made. And then we'll just do like 1 or 2 minutes each so we can kind of move through this. But yeah, so one of you guys who drew, I think you can share your screen and we should all be able to see it. So
You want
go.
group 1 first? We're going in order, or?
Let's go in order. So who was group 1? I don't even know.
I think that was us.
Okay.
My audio was off. Yeah, so I'll go ahead and share my screen.
That's a great background you got there, man.
Hey, thanks. I took that picture like last week. All right, can you guys see my screen? This guy?
Yeah, I see it.
Okay, so we looked at figure 2B with the upper layer hydraulic conductivity equals 1, lower equals 100. So this was Freeze's configuration. And so we drew lines going nearly vertical down to this lower layer with the higher hydraulic conductivity. And we just drew one big line to represent that there's a lot more flow paths down here. And so all these like follow the right angle rule, and then they go over here, they go back up, mostly following that right angle. Then we have one flow path that stays in this upper layer over there. And there may be in these recharge zones, there may be others that follow like right there, but we didn't draw them. So for this, we had all of our recharge on the right side of this diagram and all of our discharge in this basin over here.
Wait, what about this other flow path to the right? It doesn't discharge in that basin.
Who,
The
this guy?
middle flow path that stays in the low
Oh.
conductivity layer.
This big one,
No,
he's
no,
supposed to
no.
end.
The one that stays in the low conductivity layer.
Oh yeah, I guess he doesn't discharge into the basin, so I guess you could call it a spring.
Yeah, so one of the things is that not all the discharge is making it to the main discharge basin, even though
Right.
there isn't really topography to force it to do that.
Right.
All right, cool. I like it. Looks
Cool.
good to me. Next group 2. I think that's you, Amanda.
Yep, just working my mic. Okay, let's see. Clippy. So this is what we got. I couldn't get my marker super fine. Let's see if we can zoom in a little bit. Whoa. So we had 3 layers with going from low to high hydraulic conductivity and these kind of different sloping hills in here. So we got them going down perpendicular-ish to these guys and then hitting this higher conductivity zone and wanting to go along here and crossing these ones, but then eventually they go down even to this even higher conductivity zone and going along down here to where they discharge. So we kind of drew one of the big ones for these 3 different hills, and there's going to be shallower ones that don't quite make it up in the surface that go down and hit the barrier and come back up.
Okay, so one question I have here is, are there some flow paths that would make a local flow system here?
I think more towards this end.
Yeah. What about in the higher undulations? Would you see some local flow paths, say in this middle, right above where it says K1, K10, and K100? I think I could see 1 or 2 shallow flow paths that might make a local discharge.
Yeah, between these hills.
Yep.
Okay.
But the bottom line is, for the most part, if you've got high hydraulic conductivity at depth, most of your groundwater flow would be forced into these regional or intermediate flow paths, and you wouldn't have a lot of local flow.
Yep.
Say that again, sir.
If you have higher hydraulic conductivity at depth,
Uh-huh.
most of the groundwater flow it's getting forced into these deeper intermediate and regional groundwater flow systems. So that if we have higher hydraulic conductivity at depth than in shallow, we don't see much local flow. It's mostly in deep regional flow.
Okay.
Okay.
And then the other take home from your guys is that the flow will always go, even though 10 is higher than 1, the stuff in the 10 is going to want to go down to the stuff in 100. All right. So the water always heads to the highest hydraulic conductivity layers.
All righty.
All right. Breakout room 3. Taylor, you're muted, so unmute yourself.
Okay, I got it now.
Sweet.
Let's see if I can. Okay, here's my drawing. I know how good it is. Don't need to tell me. Go ahead, Jude.
So we do the pronet in the figure, which is conductivity 10 is the middle of aquifer. So I decided to draw the first point. The right angle, upper right, because elevation is high, and going down and go through under the box, and finally go up the discharge, I think, in the body. And second one is goes through the just following the previous line, and go through the middle, go through the box, and finally go to the body following the previous line. And
Yeah, so in the middle, these are converging into this high permeability zone too, right? So I think one
Yeah.
of the take homes here, and you guys have done this, is that most of these flow paths are going to head into the high permeability layer. You're going to have convergence from a bunch of flow into the high permeability layer, even though it's not contiguous. So this thing is just a little lens of high permeability. It's still, all the groundwater gets focused towards that high permeability zone. Another thing I was talking about with you guys in the breakout room, but we can see here, is your flow path that originates the farthest to the left, and then it comes down into the high permeability zone, and then where it comes out, it's not in the big basin. All right, it's discharging again, sort of in the middle of the plains, and not in the alluvial basin. So one of the interesting things here, again, we've seen it in a couple, in another place, I think we're going to see it in other places, is that you can get sort of discharge areas in places you wouldn't expect to see discharge zones, depending on the configuration of the subsurface permeability. Okay, great. Thanks, guys. So let's go to breakout room 4.
How do I stop sharing my screen? Oh,
If you, you figured it out.
All right, sweet. So group 4. So you see my so you see my figure. So we had a layer of higher permeability kind of going at a weird angle. And so kind of starting from here, we got a nice recharge going down, and then normal horizontal flow. And then I liked Peyton's example he gave of a marching army that's like running in a field, and then these people run into like a nice highway, so they start moving faster. So they kind of starts angling flow, more going down as more of this kind of makes it into more of a deeper area, and then they only pop up right in where you expect a river to be. But then this also causes this, these Ds are for discharge areas. And so we kind of see that these flow lines are popping up not in necessarily the river area, but that they don't get much, there's not much recharge area for this discharge area, like maybe kind of around here, the rest of it just kind of goes down, but this area kind of pops up, but all water that pops up here is going to stay at the surface and then maybe eventually move down.
Yeah, so one of the things, some of this is maybe freezes boundary conditions were constant head. And so it may not, if you had constant flux or a prescribed flux, which is what we have usually at the surface, really, it might change things. But this area here, yeah, it's a discharge zone, and you're right, it's not, it'd be a very low amount of discharge. It's only getting a small amount of water that sort of would be, popping up out of this high K layer. And so we wouldn't expect a lot of discharge here, but we're not adding to the aquifer system over this zone. It is a discharge zone. All right, cool. Okay, so thanks, Colton, and Group 4. So one of the interesting things about this about the Freeze paper was because he was using a computer model, all right, he could now consider heterogeneity, all right, whereas Toth had to consider this uniform sandbox. And the world is not a uniform sandbox. It's this heterogeneous, like geology happens. And so we've got all different configurations of subsurface hydraulic conductivity. And so this nice nested sort of paradigm that Toth put out, it's a really useful one to think about and to help us conceptualize and talk about different kinds of flow paths like local, intermediate, and regional. But the actual configuration of flow paths, how much water goes into the regional flow, how much stays local, it's totally dependent upon the configuration of the subsurface. And we can have all the flow in the deep regional, or we can have almost no nested flow at all, or we could have everything focused in the top layer and the local. It all just depends upon the subsurface configuration of hydraulic conductivity. And we can get really wild flow path configurations even when we have pretty simple hydraulic conductivity configurations. So a single lens of high hydraulic conductivity really throws things for a loop. Okay, great, good. That worked better than I expected. So good job, everybody. And Zoom continues to work for us. All right, so I'm going to share my screen, and we'll go back to notes. Okay, so what I want to start talking about now is unsaturated flow. And let's think about some porous media. All right, so here's my chunk, my REV of porous media, and I'm going to put some sand grains in here. So put some more sand grains in here. And then I'm going to make some smaller ones. Okay, so we've got a porous media. So these are my sand grains, which I'll give tiger stripes to. All right, and so when we're in fully saturated conditions, all right, so when we're fully saturated, all this pore space is full of water, right? And so when we're saturated, all the pore space is full of water. What was the main thing that controls the hydraulic conductivity?
Pore throat size.
The pore throat size, all right, and the connection of these pore throats. So how well connected are they? All right, so now let's think about when we're in unsaturated conditions, what our subsurface looks like. And what we'll get is zones of these pores, all right, that are full of water. So some of our pore space will be full of water. And some of our pore space will be full of air. So we have water. And we have air. Oh. Okay, and so if water was trying to move through this porous media, all right, because we've got air in our pore space, we have essentially less of the pore throats through which water can move. So what do you think that will do to the hydraulic conductivity? How would adding the presence of air change how well water can move through our porous media?
It would make it harder for water.
Yeah, it's going to be harder because there's less area, less pore throats for it to move through. All right. So in fact, the more water we have, the easier it is for the water to flow, or conversely, the less water we have, the harder it is for water to flow.
Would it be almost like heterogeneity or anisotropy?
It's a little more like heterogeneity, but it's a little different. It can be spatially distributed differently, so it can act like heterogeneity in that way. But it's a modifier. It basically just says my hydraulic conductivity will be affected by how much water I have within my porous media. So in general, we've got a few rules here. I'm going to make this bigger for June and everybody. So the hydraulic conductivity is less or is lower when there is less water. All right, so we're gonna, and another super important point is that the hydraulic, this basically implies that K in an unsaturated zone is a function of the water content. All right, and we're going to talk about why that's important and why that makes our life really, really complicated. But the bottom line is this makes life hard. So let's talk about why that is. And the first thing I want to do is start thinking about what the pressure head of water looks like near the water table. So let me add a page here. So pressure head near the water table. And we're gonna we're going to do a little thought experiment. So here's a cross section of the subsurface. And so we're in porous media. And here's our water table. Put a tree up here so that we know that's the land surface. Okay. Here's our water table. And in my, I want to do a little thought experiment. So here I've got this instrument, and it is a pressure gauge attached to a straw. All right, and that straw has a screen at the base. So this is a pressure gauge. And it's got some water inside the gauge. So I got this straw, it's got some openings, all right? It's got water in it, but the top is closed. All right, and let's make some rules here for our instrument. So let's define pressure to be positive when the water is forced into my instrument. All right, let me make this bigger. All right, let's say pressure is negative when water gets pulled out of my instrument. All right, so first of all, this idea of negative pressure, let's think long and hard, or let's at least think critically about what that means. So you're gonna, if you go on, take a soils class, or if you've taken a soils class or a plant class, we often use this word negative pressure, all right? Or tension. This also gets called tension. All right, so first of all, there's no such thing as negative pressure. All right, pressure is the measurement of atoms and how much they're pressing against each other. All right, the lowest pressure can go is 0 when you have no atoms banging into each other. All right, we are using negative pressure as a convenience here, and that is by this definition. If we would tend to pull water out against atmosphere, or if we were tend to pull water out of this kind of instrument, we call that negative pressure or tension, because it's pulling water out of this instrument. All right. So that's what negative pressure means. It doesn't mean that we have no atoms or we have somehow a negative vacuum. That's impossible. What it means is that it would pull water out of an instrument like this. Okay, so let's say I have this instrument. I put it in the unsaturated zone. What do you think is going to happen to the water in my instrument? Is it going to go out into the soil, or is it going to want, or is water going to want to come out of the soil and into my instrument?
It's going to want to pull it out.
Why?
A capillary action. The pore spaces are going to want to be filled with water. And so since we're in an unsaturated, water is going to be pulled out of the instrument to fill those pore spaces.
Okay, so capillary action will pull water out. In the unsaturated zone. All right. That means that we would classify the pressure head or the pressure in here as negative. It's pulling it out. What drives? So if we go back, if you think back to the things that controlled capillarity or the rise of water in a capillary tube, what properties were really important in controlling how high water could climb up a tube? You guys remember that?
Is it pore throat size? Pore throat size?
Yeah, so this is
Cross area.
This is a function of the pore throat radius. And if I have if the radius is low, then my capillary rise or my capillary tension goes up. So if the radius was low, my capillary rise was higher. Okay, so in the unsaturated zone, psi, my pressure head, is less than or equal to 0. It's less than 0. Forget the equals. All right. Okay, let's put my instrument now down into the aquifer. Okay, screened. It's got its gauge here, and it's got water in it. What would happen here? Would water want to flow into my gauge or out? What do you think?
Wouldn't it depend on the water table or the water level inside the instrument?
Let's say the water, good point. Let's say the water level in the instrument is lower than, this was my initial water level.
Then it would go into the instrument.
Okay. So below the water table, the pressure would force water into my instrument. Forces water in. So psi down here is positive. All right. So my pressure head is positive. All right. At the water table, at this special point, the water table, this is the definition of the water table. Psi, my pressure head, is equal to 0. All right, so we've got some really important rules here. Above the water table, psi is negative. At the water table, psi is equal to 0. And below the water table, psi is positive. Okay, we can still use head. All right, so the fluid potential is still given by the total head so it's given by the head, and head was Z plus psi, right? So it's the elevation, or elevation plus our pressure head. All right. Down in the saturated zone, our pressure head is positive. All right. And it says that my total head will be greater than my elevation. All right. At the water table, psi is equal to 0, and my total head will be equal to the elevation. Above the water table, psi will be negative, and my total head will be less than the elevation. So above the water table, H is less than Z. At water table, H is equal to Z. And below, H is greater than Z. Okay, this is super useful. We can now still use head to describe fluid flow. So flow will still be driven by gradients and potential. All right. But now we've got to take into account whether we're below or above the water table and whether my pressure head is positive or negative. All right. So let's think about how pressure head will change as a function of how much water I have in my Okay, so let's go back to our conceptual drawing of porous media. Okay. And we said that water would fill only some of these pore spaces. All right. Let's think about what happens. Let's have a thought about what my pressure head looks like in the unsaturated zone as a function of the amount of volumetric water content. All right, so if you remember, volumetric water content, what's the maximum it could be?
Porosity.
Yeah, it can equal to porosity. And
Would that be 1?
what's that? So what would my psi be right when I fully saturate all of these pore spaces? So I'm
0.
fully saturated. What's my psi if I'm not down deep in the aquifer?
Would be 0.
Yeah, it's 0 at the water table. So here's 0. So psi is equal to 0 when I'm fully saturated. All right, I start off here at this point. Now, as I get drier and drier and drier, the first pores to lose their water, you think they're the big pore throats or the small pore throats?
The big ones,
Why?
because they have less surface tension and like the capillarity is higher in the smaller pore throats.
Right. So the drier I get, all right, so as theta sub W gets lower, the smaller and smaller the pore throats are that are left that are still saturated. And so my psi gets more and more negative. All right, so I end up with this curve called the water retention curve. And it turns out that the water retention curve will be asymptotic to some level that's called the residual saturation, theta sub R. And that just says that, you know, some of these pore throats are so small that even if you don't get any rain forever, some of them are going to pretty much always stay saturated. All right. So this curve, this is called the water retention curve.
Yes, sir.
Yep.
That's by natural processes though, right? I mean, if you were to dry it, then they could. Isn't this like gravity?
Yeah, this is under gravity drainage. If you were to take this core and put the temperature up to 100 degrees, you'll boil the water off. But this is residual saturation under gravity drainage. All right, so the bottom line is the drier I get, the more negative my psi will get. All right. This water retention curve is a characteristic property of the soil. So they also get called characteristic curves. All right, and a lot of unsaturated zone hydrology is characterizing these characteristic curves or water retention curves that tell us how the capillary pressure, the negative psi, it also gets called tension, changes as a function of the hydraulic conductivity. Yep.
Is there any way, or is there some like natural like anisotropy to the way like the way that you've drawn this porous medium, like the grains are holding on to water and there seems to be like a preferential like vertical flow direction? Is that something that does occur, or does it depend on the sediment, or is it pretty more isotropic than anisotropic as far as how the water
Yeah, it's far more like what I've drawn, and
Okay.
in general, we would expect anisotropy, and we see a lot of preferential flow, but we're gonna ignore that because it gets too complicated to work with.
Okie dokie.
So there's a couple ways that we characterize these curves. All right, and we're gonna there's like a cottage industry of characterizing these curves, but we're gonna talk about two major characteristic curve types. So now I'm just going to put the caveat. We're going to talk about the two most popular ones. Literally, there's hundreds of these in the literature, and everybody defines their own. But we're going to talk about the Brooks-Corey and the Van Genoegden. All right. So here's the thing. First, we're going to define this term effective saturation. All right. And this is just a normalized saturation. And it looks like the equation. So effective saturation is S sub E. And it is equal to our measured theta minus the residual saturation over N porosity minus the residual saturation. All right, so effective saturation, the max it can be, well, this can be a max of 1 or max of N. So S sub E can vary between 1, all right, or this can go to theta sub R. So this could be, so S sub E can go between 1 and 0. All it is a normalized saturation. All right. So for the Brooks-Corey equation, the relationship between these two S sub E colors is equal to psi sub B over psi to the lambda, psi less than psi sub B, or 1 psi greater than psi sub B. All right. Psi sub B is my air entry pressure. This is the air pressure it would take to bubble air into a saturated porous media. All right, so it's the amount, you can think about it as the minimum amount of capillary pressure. All my pores are saturated and I want to desaturate it. How much pressure would it take? And lambda has something to do with the pore size distribution. So that, Amanda, kind of takes into account this idea here where some of your pores are going to be saturated and some are going to be unsaturated. this lambda is a fudge factor that deals with that pore size distribution. All right, so this is Brooks-Corey. This is a one of the most famous ones. And then just real quick, this is the other really famous one is the Van Genuchten. And the Van Genuchten, we have SE is equal to 1 over 1 plus alpha psi beta to the gamma. So alpha and beta are fitting parameters. So they're just empirical. They're just empirical constants that we get from looking at curves of psi versus beta.
So is that a division? Alpha?
No, this is the absolute value of psi. So alpha times the absolute value of psi to the beta.
Okay.
And then the gamma is just equal to 1 over 1 divided by beta. Okay, so these are my two equations that will give me a characteristic curve, all right? So if I wanted to look at what effective saturation I would need to give me a given psi, I would just say, take a bunch of psi's, plug them into this equation, and I could calculate a bunch of effective saturations, all right? So one of your assignments in the homework is to calculate effective saturation or characteristic curves for a couple different porous media, right? And it's basically, you got to plug this equation into Excel. I would do it for a bunch of different psi's, all right? And then you get a bunch of different SEs and you just plot SE versus psi. Really easy. So before we go, just a quick bit of business. Right now, the syllabus says homework is due the 2nd. All right, that is, I believe, next Tuesday.
Thursday.
It's Thursday? Okay, great. So homework is due next Thursday. Tuesday, we'll go over relative permeability. And you should have, I think, everything you need to do all the problems and all the homework. If you need, so I know some people have requested an extension on homework because they've had to travel and life's been crazy. All right, life's been crazy for all of us. I'm happy to grant extensions as need be. I don't want them to get too far because I'd like some time to be able to grade these and get them back to you so that we can have our exam. And I want to try and keep as possible on schedule. We're being encouraged to even try and finish our classes early if we can. So this is really hard for me because I always end up at this class just wanting to like have another semester to teach you guys more. So I'm going to try and get the basics of what I want you guys to get out of this course in as fast and as efficient as possible. But, you know, I still want you to be able to go out in the world and know what hydrogeology is. So bottom line here is, for now, homework is due Thursday. If you need an extension, talk to me. I'm willing to be flexible. All right. But let's try, if possible, to stay on target. I know things are crazy, but I do think when things are crazy, trying to keep as much of our schedule intact as possible helps us with some amount of routine. But that being said, I will of course adapt to people's needs, and I already have done that, so it's an option for everyone.
Hey, sir.
Yeah,
Office hours after this, is it the same code?
it's the same. All the office hours will be the same code as I sent out. So
Okay.
if you need that code again, just email me.
Is there a Dropbox for today's freeze worksheet?
I thought I put one up there, but I don't know for sure. I'll make sure there is one. If there isn't, I'll check right after class. If there isn't, I'll make sure that there is one within the next few minutes. I thought I put one up, but Lord only knows what I've actually done and what I haven't. So I'll make sure it happens. Any other questions? Okay, have a good weekend, and we'll talk to you guys soon. Cheers.
Thanks, Peyton.
Thank Ben.
Thank you.